Hello and welcome to the second part of the Linux binary analysis course by EC Council. In this section, we will examine software security techniques that may be used in malware or protectors. The first technique that will be reviewed is anti-disassembly. Well, what's that? If you can confuse the disassembler's engine to do its work on the wrong offset, and the valid instruction could be hidden from the eye of analyzer. Anti-disassembly techniques work by taking advantage of the assumption and limitation of disassemblers. So if you want to understand how anti-disassembler techniques work and how they are made, we need to understand how a disassembler engine works. Generally, there are two types of disassembler algorithm, linear and flow-oriented. The linear disassembly algorithm is the most simple and also the easiest to implement. But this method still has many problems because when it wants to disassemble a region, it considers all bytes in that area to be code and attempts to disassemble all the bytes. Because of this, it's easy to defeat. The flow-oriented disassembly method is much more accurate than linear disassembler because it follows the same code execution flow and it's not linear and blinded. As a result, it's easier to distinguish data between codes. Most commercial disassemblers, such as IDEA Pro, use this method. IDEA uses recursive distant disassembler technique, which is based on the idea of flow-oriented technique. The key aspect of this method is that it classifies the code and analyzes each class differently. For example, when it comes to a conditional branch, there will be two branches to analyze. So it will choose one and proceed. It will also place another branch in a queue until it returns and analyzes the remaining parts. Using recursive descent has the disadvantage of being unable to follow indirect paths like jump and calls that use a table of pointers to locate a target address. However, neither approach is completely accurate. I've prepared some common technique that you might be facing. Now, let's analyze the source code and see what's happening when we disassemble the binary file. You can use the build anti.sh file to build the source code. Okay, when we run the compile file, we can see it's a simple hello world. And there is no problem with strace, it works properly. Now let's check the source code. This piece of code is the data section, and here is the text section, and our entry point is the start label. In the main function, at the first, anti-disassembly function number 1, 2, and 3 are invoked. After that, there is a simple technique, and then anti-disassembly for a function is invoked. In the main function, at the first, anti-disassembly function number 1, 2, and 3 are invoked. After that, there is a simple technique, and then anti-disassembly for function is invoked. Now, there is some junk data that never be executed. We will see why that happens later. Our main code that prints the message on the console is started from the continue label. Again, there is a very nice and interesting anti-disassembly trick between printing the message and exiting the program. Let's check and reviews from start. I will comment all tricks and analyze all of them step by step. In the Anti-Disassembly function, and there is a junk byte among the instructions. As said earlier, the linear disassembler can distinguish between data and code. So with this technique, object dump as a linear disassembler will have the wrong output. Now let's build and check the compiled binary file with IDA and object dump. So we can see that the trick works. The output of the object dump is incorrect and treat the byte as code. Now check the file with IDA. As we can see, IDA disassembler is not confused. What happens if we change the unconditional jump to a conditional jump? Let's give it a try. So as we can see, IDA disassembler is also confused. As a flow-oriented disassembler, IDA can understand the difference between data and instruction, and identified the anti-disassembly one as a procedure or function. However, if you change the unconditional jump to a conditional jump, IDA gets confused. Moving forward and check the next function, that means anti-disassembly2. As we can see, IDA disassembler is also confused. As a flow-oriented disassembler, IDA can understand the difference between data and instruction and identify the anti-disassembly one as a procedure function. However, if you change the unconditional jump to a conditional jump, IDA gets confused. Keep moving forward and check the next function, that means anti-disassembly2. Pony malware uses this trick, which is a bit interesting. Like this, you can also change the return address at runtime to confuse the flow-oriented disassembler. After we call this function, the return address will be in the stack. As you can see, the real label address is pushed to the stack, so it will be at the top. We can consider it as the second return address. So the first return instruction will jump to the real label or second return address, and the real label only have a return instruction that will jump to the first return address. Let's check it with IDA. Well, there is the first sign of error. We cannot see anti-disassembly2 in the function window. We can now see that the second return instruction is recognized as data. Now let's examine how the anti-disassembly tree function works. After anti-disassembly label, here we have two conditional jump that refer to the same place, and again there is a jump byte among instructions. After that, we use the indirect branch technique. So we have the address table with our pointer table, and I'll look up the destination address through this table. As said earlier, flow-oriented assemblers have challenged with the indirect branch technique. Here, the two conditional jumps confuse the disassembler so that it couldn't recognize the junk or data byte among the instructions. Now let's change this jump to the unconditional one and see what's happening. We can see that nothing was changed in the function window. Start. Here the junk byte is identified, but the disassembler engine can't understand the flow correctly because of the indirect calling. Since our function doesn't have a written instruction as a regular function, the disassembler is unable to locate the end of the function. There's a simple trick that adds the address of the current command and the number 3 to get the destination address of the jump. And this command is 2 bytes in size, and 1 byte is junk. This is why the number 3 has been added. In the Anti-Disassembly function, we have the same technique as previous ones, but different instruction. The indirect branch technique here can happen in two ways. First, we can push the continual level address directly to the stack, and in a second way, we can use address table for getting the continual level address. Then we can push it to the stack and make the flow more complex. After printing the message, there's a nice trick. In the GZ instruction, we can see the subtract sign, which means jump backward. If we jump back 4 bytes, we will be on the EB05 byte. That means here. EB05 is equal to unconditional jump to 5 byte forward, which means after the junk byte. And that means here. In this trick, we jump to in the middle of the instructions, which is confusing. Let's give it a try and see what idea does with it. You can see we only have the start in the function window. Now let's uncomment this part and build it again. And you can see we only have the Anti-Disassembly in the function window. Where is the start procedure? It's here. Okay, we can see that, and the disassembler identifies everything after the read instruction as data, and we stop everything because of this simple trick. In this video, you got familiarized with different anti-disassembler techniques. Now you can recognize them in your analyzing process, or with a bit of creativity, you can create your unique technique. In the next video, we will examine anti-debug techniques. Until then, have fun with the assembly instruction and disassemblers.